Hello, let's look at this linear first order differential equation with the initial condition. But this initial condition look strange, right? It gives you y of 0 equal to a. It doesn't give you any specific value a. So here a can be any value. So you can think a as a parameter. Okay? A can runs over any value. Okay? And the question is, find the specific solution for this initial condition, so in general in terms of a, and then for any initial value, let's say for y of 0 equal to 1 or y of 0 equal to 2, etc. For any value of a, you can just substitute a equal to 1 to find the specific solution for this one, right? You can substitute a equal to 2 to find the initial the solution for this initial condition, and so on, right? And then the actual question here is, is there any critical value of a, is there any important value of a for which the solution distinguish between two sides? Okay, it's like very similar to what we did before with the c. um, so is there any critical value of a, so that when a is bigger than that critical value and when a is less than that critical value, there is some character differences between the solution of these two group, right? Is there such a value of a? If yes, approximate that value using a computer or maybe some algebraic technique. So this type of question, of course, you need a help of a computer, especially GeoGebra, or some other software that you are familiar with, and then of course you have to do some algebra by hand. So let's do that. So let's divide both sides by 2 to make it a standard form. So this solution should be easy. So let's find out. So in this case, the p is negative half. Remember, you have to include the sign on the left. The q is the right hand side. So u is e to the power integral of p, which will be e to the power negative half t. We do not add any c at this point. So let's solve for y. Let me write the formula. Integral of u q dt, that goes on the top, and in the denominator I have u. So the integral of u is this, and the q is this, right? Let's just substitute all of that. So I substitute u and q divided by, of course, I also have to put my u in the denominator. Continue. I can multiply out e to the negative half t and e to the t over 3, right? I can multiply. And of course, when I multiply, you add the exponent, right? So let's do that. And this half, I can bring it outside the integral. So let's do that. So I bring half outside. Okay. Let's do this. Let's do this multiplication here, so nobody get confused. So I'm adding, right? Negative half t plus 1/3 t. This t over 3 is 1/3 t, right? Um, make the denominator same, so I can multiply by 3 here, top and bottom, and I can multiply by 2 here, top and bottom, right? So this is actually negative 3 plus 2. So what I get is e to the power negative 1 over 6 t. So this is negative 3 plus 2, which is negative 1, and the denominator is 6. The common denominator is 6. So here I get e to the negative 1 over 6 t. and that's the integral, don't forget that. So I have to put the integral dt. Let me actually write it here, divided by e to the negative half t. So let's do that. Again, if you remember, we use this general formula, integral of e to the at, where a is some number, right? It's going to be 1 over a e to the at, and of course plus c. So let's do that. So let's use that. Y equal to 1/2 I copy. In this example, this negative 1 over 6 is like my a. So what I'm supposed to have is 1 over a e to the at. This negative 1 over 6 is like my a plus c. But this one, it can of course simplify, right? Keep, change, flip. So here 1/2 times, I flip negative 1 6, so that become negative 6 over 1. So that's actually negative 6 over 2, which is negative 3. So I get y equal to negative 3 e to the power negative 1 over 6t plus c divided by e to the negative half t. You can distribute this in e to the negative half t. So let's distribute. I can simply write c e to the half t. If I bring that negative half t in the numerator, it becomes e to the half t. So this e to the negative half t become e to the half t in the numerator. Here, you're going to subtract. You're going to subtract the exponent, right? So this will be. So let me copy negative 3, and you subtract, right? So it's negative 1 over 6t minus negative half t. So it's actually a 2 negative, make it a plus. So let's continue that. So it's actually negative 1 over 6t plus half t. So I show you all the work, even the simple addition and subtraction of fraction. So I get negative 1 over 6t plus 1/2 t. And let's do that here. I'm going to multiply this by 3 to make the denominator same. So this is going to be negative 1 plus 3. So if you combine them, right, this one, if you just concentrate on this one, this is just negative 1 over 6 plus 3 over 6. So that's just negative 2 over 6. Negative 1 plus 3, I'm sorry, just 2. Positive 2, sorry. So negative 1 plus 3 is 2 over 6 t, or 1/2 t. Sorry, 1/3 t. Okay, 1/3 t. Okay. So what I get here, so let's write the final answer here. The general solution is y equal to negative 3 e to the power 1/3 t plus c e to the power 1/2 t. So that's my general solution. Let's substitute the initial condition. So my initial condition is y of 0 equal to a. So let's do that. So my initial condition is y of 0 equal to a. In other words, when t is 0, y is equal to a. Let's do that. So I'm going to substitute a in place of y and substitute 0 in place of t. So if I substitute 0 in place of t, right, e to the power 0 is 1. So all I end up with is negative 3 plus c, or c is a plus 3. So I can put this a plus 3 in place of c. So that will be my specific solution. Of course, a is some given number. Uh, the question does not give you a specific value of a, so you're thinking a as a parameter. So a can take any number. So here, my specific solution is given by y equal to negative 3 e to the power 130 plus, I'm going to replace c by a plus 3 e to the power half t. So that is my specific solution given in terms of a. So now you're thinking a as a parameter, and let's graph this in the GeoGebra and see, is there any specific critical value. You can probably guess, right? Just looking at it, right? Just looking at this factor, right? When a is actually negative 3, this part completely vanish, right? You end up with only this part. So there may be something going on when a is bigger than negative 3 and when a is less than negative 3. We might expect a different types of behavior when a is bigger than negative 3 and when is a is less than negative 3. So let's check our intuition and see if that is exactly the case. Or maybe we can find some other value of a. We never know. So let's think about that. So let's do that. Okay. So first I'm going to create a slider for a in the GeoGebra, and then we're going to plot this solution, and we're going to slide the slider of a, and in particular we're going to pay attention when a is equal to negative 3. Okay, so let's do that. So I'm going to open my GeoGebra. So I'm going to use a slider for a. So I write a and enter. Here let's oh, I can, if I do that, I can actually slide here on the panel, but it's okay. No. And then I have the specific solution in terms of a, which is negative 3 times e to the power 1/3, e to the power 1/3 e plus a plus 3 e to the power 1/2 t. Very good. Let me change the color red. I like red. Okay, and you can slide the a and see you get a solution, different solution, of course, right? Okay, all of them are solution to this differential equation. So for this one here, that's the solution for the initial condition y of 0 equal to 0.5, right? So this is the solution. Let me see if I can. Okay, so this is the solution here, right? That's for the initial condition y of 0 equal to 0.5, right? You can see the 0.5 here. That's my 0.5, right? So you probably get the idea, right? If I use a different a, okay, for example, this one, that's a solution of the initial. So this one is a solution of the initial condition y of 0 equal to 1.8, right? Which is this one. if you think about graphically, right? If you think about this initial condition y of 0 equal to a as a point, this is simply as a point, this is simply 0 comma a, right? So if you look at our, where is 0 comma a, I'm just going to actually put 0 comma a, so you can see 0 comma a. At this point my a is 1.8, and you can see my 1.8 here, right? uh, and the function goes to this 0 comma a, and when I change the slider, the a will move and also the function will move, but a is always on top of that function, of that solution, right? Because it's supposed to go through the initial condition, it's supposed to satisfy the initial condition. So this is supposed to go through the point 0 comma a, right? For example, at this moment my a is -1, so my function should go through 0 comma -1, and it indeed that is the case. Okay, so I'm going to change the range for our slider to -10 to 10 to get a better picture. Okay, good. Now let's see what happened if I slide. Okay, let's do on the negative side. Something going on here, right? See, let me actually zoom out. So maybe we can actually zoom out to see the behavior, right? The whole holistic view. Okay, if I increase at some point, oh, look at that. Look at that. Oh, so that's the change of the behavior, right? It goes from the up to down and down to up. So where that happened, okay? If I go here, we suspected it should be probably a equal to -3, uh, but it looks like may not be. um, but let's see, is it a -3? Let's see. It's maybe, I don't know. So let's see what happened if I put a equal to -3. Let's put -3. Oh, it's probably -3. Okay. Let's see if I put -3.1. Oh, it doesn't change. So there may be some other. It's not actually -3. It's actually, so we thought it's -3, but it's not actually. Okay. So so sometimes our guess is looks like it's something -2.8. It's maybe it's very close to -3 actually. Uh, Perhaps it is -3. Let's put some example. Negative. Uh, let's do -2.9. Oh yeah, I think it's -3, because even -2.9, I get a different types. Even I get a um, uh, I get this one. So you can actually go and see how it looks like, right? Yeah, it is actually -3. How about -2.99? Still, I know the graph goes through the top, right? It comes back to above x-axis. But once it is below -3, let's say -3.01, then it will stay below. It never come back. Yes, so our guess is actually correct. So there's the critical value of a is a equal to -3, right? So if you want, the critical value is actually a is equal to -3 when a is bigger than -3, right? The graph will eventually come back above x-axis. So for example, when a is -2.9, which is bigger than -3, right? The graph will eventually come back. The graph will actually go down and come back, and goes above x-axis, right? Uh, you can see that, right? So I zoom in, right? So that's my critical value. A is -3. As long as a is bigger than negative 3, the graph eventually comes back above x-axis. And when a is less than negative 3, the graph does not come back. It just goes down. It's always decreasing. And when a is bigger than negative 3, it has a local minimum. It has actually a minimum where the graph actually turns back and goes up. So when a is bigger than negative 3, the graph has a local minimum, actually global minimum. The graph has a minimum and it goes above x-axis. In other words, the y goes to infinity as t goes to infinity. So that's how to happen when a is bigger than negative 3. And when a is less than negative 3, the graph always decrease. The graph always decrease, and it doesn't seem that there is a minimum. And we know that in that case, y actually goes to negative infinity as t goes to infinity. So that's a very different behavior when a is above negative 3 compared to a is below negative 3. There's like a different types of behavior. So that a equal to negative 3 is actually a critical value. Always remember that you can do it. Bye bye.